Welcome to the CREDC seminar series. Today we're having Dr. Roger Schell, who will be talking about reducing the attack surface in a leveraging an integrity max security kernel. Now what that means, it's a mandatory access control security kernel. Think of it as a very secure operating system, and in this case implemented on programmable logic controllers, or PLCs. As you may be aware, PLCs are used in many control applications in, for example, electrical substations. And reducing the attack surface means coming up with access controls between aspects of that operating system kernel, as Dr. Schell will describe, so that there's very little left to tie down, and you understand very well what remains to be tied down. Dr. Schell has a PhD from the Massachusetts Institute of Technology and has extensive experience in government and industry in the cybersecurity space, including as founder or co-founder of a couple of cybersecurity conferences. He has received awards from NSA and NIST, and he was involved in the Orange Book, which only a few of us graybeards will remember. And he's a retired U.S. Air Force colonel. He's in the National Cybersecurity Hall of Fame. I was not even aware that that existed, but congratulations, Dr. Schell. And with that, I will turn it over to you.
Well, good afternoon. I appreciate the opportunity to describe some of the research results that we've had. And at the end, I will provide an opportunity for questions if they want to pass those through you, or if there are questions from the right. So the outline for my presentation today is we'll spend a little bit of time, not a lot, talking about the problem of cybersecurity for energy delivery systems. And we'll spend most of our time talking about the solution technology that we have used and the approaches we've taken in our research results. We've been actively working on this for half a dozen or so years, and the results have shown up in a couple of different ways. Most recently, I was on USC faculty for a couple of years, and there was an active project there that I've continued on here along with some of my associates there. And then we'll wrap up talking about the delivery path for technology transfer. How could these results be incorporated into products that can actually be out there in the field? To start with, I'll review briefly the risk associated with this, with cybersecurity, and particularly looking at the problems of resilience and vulnerability to cyber-physical components. This is just a couple of reminders from the press, nothing new here. But this year, people have commented a couple of months ago, Leon Panetta at an RSA conference was asked what he was concerned about. And he said his biggest nightmare was an attack that disables the U.S. infrastructure, and particularly talking about the energy delivery infrastructure. And he has opined that this could result in millions of lives lost. And so that seems to me to be a big enough concern that it's worth our giving some attention to in terms of the need. More recently, last month, both the current and former CISOs were asked what kept them up at night at a conference, and they said the exposure of the critical infrastructure to attacks against industrial control systems, and the PLCs are an example of industrial control systems. And from the press, we see that a report the U.S. government believes that there is Russian subversion, that some of the hacks a while back to our power grid didn't cause any actual damage to the systems, but the belief was that the hackers left behind tools needed to later disrupt the system. That is what I'll refer to here, and literature referred to as the problem of subversion. And in terms of this risk, one of the major issues, and the one which seems to be at the heart of anything that's going to like lose 1 million lives, is physical damage to the critical devices that are in the infrastructure. And so that's what we've really focused on here, is preventing physical damage and destruction. Things like generators and large transformers and things like that are devices which would take a long time to replace and hence could cause long-term impact if they were physically damaged or destroyed. We just note that computers all have an operating system, not a surprise, but programmable logic controllers or industrial control systems also have operating systems. And what science tells us, one of the NIST publications points out, that it's just scientifically impossible to build a secure system without a trustworthy operating system. You can't build a good castle on a foundation of sand. And just observe in terms of the risk we're at today, that the energy delivery systems today widely use PLCs, but that none of these PLCs are on a really trustworthy operating system. The truth is that there are only a few operating systems that are widely used. The usual names of Linux and Microsoft and Wind River account for the large majority of these. And why do we say these are untrustworthy? Well, they each have a stream of security patches that come out, and so clearly they're not really a trustworthy operating system. And we have evidence of reported events of the cyber attacks directly inflicting permanent physical damage when they occur. Stuxnet, of course, is well known, was deliberately intended to destroy the Iranian enrichment centrifuges and did so successfully. Another attack called Crash Override was recently reviewed from Ukraine, and the conclusions were that it was intended to engage in physical destruction in the Ukraine power system. And Triton was another one from a while back that was aimed at physical destruction at a Saudi refinery, according to press reports. And so what we see is that the attackers, the reason this is a national problem is because we have adversaries which set about to cause physical damage, and the physical damage can have long-term impact on the society, and so it's been characterized as a national existential risk. Nothing new there. Those are things that most of you are aware of. So I want to move on to the solutions and how we've approached addressing these problems in our research. We have used an open source project called OpenPLC, which provides a running PLC, and that runs on Windows or Linux, and it allows us to provide controls to a physical device. We've ported that to run on a security kernel, and I'll talk about some of the changes we've made to it to run on the security kernel. And that's really the tool that we've used in our research to say, what does a PLC do? We're not PLC experts, but we've used this open source code and we're running that, and we've used it so that we can have somebody at a linked computer give commands to the PLC, and those commands can show up in physical outcomes that we can see happening. And we have that running in our laboratory. Now, I want to introduce the notion of the security kernel technology. Notion's been around a while, but not everybody may be familiar with the term. The seminal description was in 1972, and it was described as a compact kernel of operating system and hardware such that an antagonist could provide the remainder of the system without compromising the protection provided. And that's really at the core of what we're trying to do when we say reduce the attack surface. We want that most of what an antagonist could attack simply wouldn't compromise the protection of the underlying physical device. A decade later, that was summarized in an IEEE article. And the thing that article noted was that it was designed to be effective against attacks that the designers had never considered. That's different than how some people view dealing with adversaries or attackers. Well, you have to know what their attack is going to be, and then you go out and you thwart it. But the security kernel was designed from a different point of view, since it said, okay, the antagonist can provide the remainder system without providing a protection. That doesn't presume that you know what the antagonist is going to do. And so a strong characterization with the security kernel is that you don't know what the attacks are, that it's designed to defend against attacks that you never even considered in the design. And you might say, well, have these things ever been used? Well, the reality is that over the last number of decades, half a dozen security kernel-based operating systems have run for years, even decades, in the face of nation-state adversaries without a single reported security patch. Now, that isn't a proof of trustworthiness, but it's certainly an indicator. When you consider that, as I noted earlier, essentially all the industrial control systems in use today in our critical infrastructure are on untrustworthy operating systems. They have routine security patches. And yet these half a dozen kernel-based operating systems ran for decades, very high-profile systems in some cases, without a single security patch. And so that says that we believe it's worth considering seriously as a candidate for the basis for our programmable logic controllers. The concept was looked at in the early 70s. ARPA had a review group, and they said, well, how can we really deal with the problem of computer security, as they called it then? And the conclusion for that group was that the only way we know to build highly secure software systems of any practical interest is the kernel approach. And I think it's pretty much the case that that's still true today. After a decade or so of that experience, including some of those early deployments, NSA was given the charter to provide a computer security center to enhance the availability of trusted products on a national scale. So the question, what do you mean a trusted product? So they codified the results of the previous decade or so of research into a typical kind of technical standard called the Trusted Computer System Evaluation Criteria that here's what you have to do, and we can evaluate against this criteria. And their highest class, the only one intended to deal with this problem of subversion and such as that, was called Class A1. And in their glossary, they defined the security kernel as the hardware, firmware, and software elements that implement the reference monitor concept. And I'll talk a bit later about the reference monitor concept, which NIST addresses in some of their publications. So what is this security kernel? Well, you start with some hardware platform. Typical kind of hardware platform, except that one of the things that came out of the results and even preceded that early research was that you have to have certain hardware features to make an efficient base on which to provide a verified security kernel. And the two parts of hardware that were identified during the early research at MIT and Bell Labs in the Voltage Project were things called segmentation and protection rings. And it's indeed the case that of those deployed systems that I mentioned, all of them were on a hardware base that had segmentation and protection rings, not because they were commonly available at that time, but because it was the only way they knew how to provide a verifiable security kernel was to build it on a hardware which had those capabilities. So around that hardware, you then build the software that makes up the security kernel, and it's designed to meet this Class A1 criteria that was put together by the government, by a lot of industry participation, international participation. There were actually translations of that into multiple languages. It really represented the codified knowledge of a decade or so of work on how we can get a truly trustworthy operating system. That combination of hardware and software into a package is what we've called a trusted device. And on top of that trusted device, you can then put an application in the sort of way that you would run on an operating system. And one of the things that you could run is a programmable logic controller. And that's what we've done. We've taken an underlying trusted device implementing a security kernel with its API, which is just an operating system interface. And we've ported the OpenPLC source code to run on a different operating system. It already was running on two operating systems, Linux and Windows. And so not fundamentally a big deal to port it onto another operating system. And that's what we've done in our research. The difference is that is really a paradigm shift for that kind of application, because they're running on the security kernel, which run in various forms of security kernels have run for years without a security patch. And the other operating systems that are commonly available simply don't have that property. The property of finding and fixing is one which an IBM executive several years ago described as an arms race we can't win, because we're not able to find and fix all the holes. That notion of a kernel-based solution is sufficiently important that over the last number of years, NIST has concentrated on they've described as their flagship security engineering guideline, something called their 800-160. And that specifically calls out the value of a kernel. They have a call-out section early in that document on the electric grid industrial control processes. And in that call-out, they note that, as an example, that you can have a highly assured kernel-based operating system in a programmable logic controller. And that's exactly what we've done. We've taken that NIST guidance and we've used that in our research, and that's exactly what we provide is something that does what they suggest. We have a kernel-based operating system in a programmable logic controller, the OpenPLC. And they go on to say that what that kernel-based operating system can do is to help achieve a high degree of integrity over through domain separation, security domains, if you will, with control of cross-domain flows using shared resources. And again, the mandatory access control, I'll talk a little bit more about that, is exactly about providing that access across domain and managing domain flows. And so we've used the kernel-based operating system to do exactly what NIST recommended doing for a high degree of system integrity. So the overall approach that we've taken is we're controlling sharing between integrity domains, enforcing the mandatory access control, and the verifiable design of that security kernel could be built, you might approach that in one of two ways. We note that the typical thing that has been done for years is adding on security. You take an operating system and you add on to it with a set of security patches and updates and that sort of thing. And the trouble is that that path of security by test and analysis has failed and will continue to fail. You never know when you're done. You're never finished. You're waiting for the next bug to be discovered and the next patch cycle to come out. The alternative to that is the one which we've taken, which the security kernel approach uses, is to build in security by construction. And that is the reference monitor base that the PCSec advocates. And it is specifically designed to mitigate malware. So we have a verifiable design. We have a design which deals with the problem of malware, things like Stuxnet. And all three of these requirements, the access controls, the verifiable design, and the subversion control, are required to have a secure operating system that is a security kernel. I've called that, in a paper I wrote a couple of years ago, the cyber defense triad. As these, think of it as a stool with three legs: the map policies, the verifiable design, and the mitigation of subversion. Well, that's the foundation on which we build this approach of a, as this calls it, a kernel-based PLC. So that's sort of an introduction to the notion of a security kernel. It's basically an operating system. It is an operating system. And I mentioned the three properties of the MAC, the access control, the verifiable design, and the subversion mitigation. And so we'll look at each of those more specifically, and starting with the access control policy. For the OpenPLC approach that we've been having in our lab, we've identified 4 distinct hierarchical integrity domains. And what we mean by hierarchical is each one, number 1 is higher than number 2, et cetera, down the list. And the most high integrity domain is the cyber physical domain. It's the only domain that has the ability to use the hardware to physically issue I/O commands to the physical hardware. And it has in that domain the ability to run certain processes that are unique to that hardware. Senior scientist at Sandia has, named Lyndon Pearson, has talked about a safe region. He says if you look at the possible state space for that physical device, you're able to talk about the part of that state space, for example, power generator, the speed in which it should operate, which is safe for that. That's the safe region. And with a small amount of an application in this safe region application, you can ensure that that generator never goes faster than that speed that it's designed for. That code and that application and the physical access to the device all occur in the highest integrity domain, which is the cyber physical domain. Below that, it is driven by data from the SCADA domain. If you're familiar with the way PLCs are constructed, they almost a quintessential property of PLCs is that they have a logic loop. And that logic loop is part of the SCADA domain. It's the thing that actually goes through and decides what the functions and features and capabilities of the PLC are. That logic loop, of course, is driven by input that comes to that, and that's the third domain, which is the distributed controls, some sort of network interfaces that allow access to that logic loop and connect typically to other components. In today's PLCs, they don't just sit by themselves in an island typically, but they're part of some network. And that distributed control typically doesn't have its own dedicated network. It uses untrusted public networks, i.e. the internet. And so that becomes the fourth hierarchical domain that we use for purposes of approaching this. So if you think about that in terms of attack space, well, we have at the end of the day these critical physical devices. They're not all the physical devices in the energy delivery system, but those critical ones that cause this national crisis. That physical device we want to protect from physical damage. If I look at what's done today with an untrusted operating system, the reality is, as demonstrated by any of the attacks I listed and ones that are many that I haven't listed, if I have access to a public network out there that's connected to that physical device, there's nothing but wires and operating systems between them. And so I, in fact, have the ability to attack from the public network the actual physical device itself. So if I look at something like the crash override in Ukraine, I can, from a public network, mount an attack that ultimately can destroy devices in the energy delivery system. And this is the usual picture you see, if they had the reality of it, of the PLCs that are out there today. It's just, that's why we have patches all throughout, but the patches are spread throughout this whole attack surface. Well, I can reduce that attack surface to deal with just the distributed control thing. For example, if I, instead of running my energy delivery system on a public network, I had a dedicated network for just the industrial control systems. In fact, if you look in the press, you'll see that there's been a fair bit of attention recently of people proposing that, what I consider a rather ill-conceived approach to deal with the problem. And so that still leaves a rather large attack surface, but it reduces it somewhat from the total public network. I can reduce that further to just the control systems that are, say, the logic loop and the things associated with that inside the PLC, the SCADA controls. And that reduces the attack surface yet further, but I no longer really have a very effective energy delivery system because I just sort of have an island to itself, the PLC controlling the device. And I can even control that more tightly by just having the controls directly for the physical device. Back in the day, the logic loop came about because there were electrical logic actually controlling the devices. My training is an electrical engineer, and that's how we would have gone about engineering something to control something like a generator with logic, and it's not connected to anything else. But that's not the world we live in. It's not a very useful energy delivery system. So that's the four domains that we've identified. And what we propose to do is to use the mandatory access control to, as NIST describes it, control the flow between those domains. And so we still have everything running on the same physical platform, from the physical network interfaces all the way down to the physical device, are on the same security kernel. But I use the mandatory access control, the integrity MAC, in order to enforce these integrity domains. If I now overlay that on top of the OpenPLC, this is sort of a diagram of what the OpenPLC offers. They have on the far left the control of the actual physical device. In our high integrity domain, we have decomposed that OpenPLC into these integrity domains. And on the high integrity domain, it's the only domain that can actually access the device, and which is the application for the Pearson safe region control. In the medium integrity, I have the quintessential logic loop for a PLC, and it's taking its command from the medium-low integrity that interfaces to the actual network control. That medium integrity includes the SCADA controls of various form. The network provides input to them, and ultimately that input comes out over the public network, if you will, the internet. The dotted arrows represent the cross-domain flows that NIST talks about, and we'll talk about those in a minute. So this is how we have decomposed the OpenPLC functions and allocated them to these 4 hierarchical integrity MAC domains. So since our real focus is on protecting the physical device, I want to look at the 2 left domains. On the far left, we have the physical device. These processes and databases are straight out of the OpenPLC source code. We've just simply taken from, they have a buffer management that has a database that has data in and out from the logic loop that goes to the physical device. And we put that into a separate high integrity domain, and included in that domain, the Pearson safe region application. The medium integrity is they provide, right out of, we just took their source code and just simply ported it. It represents the logic loop. And it's got the buffers and the databases that go with that. And we've just simply ported that onto the kernel operating system to perform those functions. And we've added, at the bottom, you see this cross-domain service, which provides a very constrained pipeline between the medium integrity and the high integrity control, that the commands can only go across there. Because of the nature of the mandatory access controls, the medium integrity can read the data that's on the high integrity without problems. It doesn't have to go through anything special, because I can't cause damage by just reading the database. And so it updates its logic loop databases by just reading directly those databases. This same pattern is then replicated for the rest of the domains as well. But it illustrates essentially the core property of what we've done in our research is to port this open source to run on a security kernel, implement the same functions, but to decompose that OpenPLC source into these 4 integrity domains. So, for that to be effective, well, those integrity domains have to be enforced in a verifiable way. Doesn't do me any good to not only have those domains if I really don't enforce them. So that's the verifiable domain for that MAC enforcement. Again, NIST has addressed this problem of getting that high assurance, and in that same flagship guideline, they have an appendix that talks specifically about trustworthy secure system development. And in that, they reference the reference monitor concept, which was also, you may recall, noted in the definition from the TC set. And it says that the reference monitor provides an abstract security model of the necessary and sufficient properties that must be achieved by any system mechanism to claiming to securely enforce access controls. And of course, the implementation of that is the security kernel by definition. And the access control that we're enforcing with the reference monitor is the integrity MAC access control. So again, we're very much following that NIST guideline and implementing that in our OpenPLC project. So how do I get that verifiable design for MAC? What I earlier called secured by instruction. Well, I start with the security policy. Our security policy is the integrity MAC policy. I have to write that in a way in which I can actually formally verify properties about the policy. That's something which the TC set calls a formal security policy model. That's a term of art. It is the linchpin for the rest of the notion of the security kernel. It is the thing that allows us to know exactly what properties, from a policy point of view, the security kernel will implement. And in particular, it has something called a basic security theorem. And what that theorem provides is a proof that following that model, the only information flow that is allowed is that authorized by the cross-domain flows for the integrity MAC. That's exactly what we want to have verified for our approach to work. That security policy model is, of course, just mathematics. It has to be put into something that is a specification that you can actually code to. And although it's mathematics for what the kernel API does, it needs a specification. That's something that's called a formal top-level specification. It's just the specification for the security kernel. But I can't run a specification. And so I have to translate that into a set of design documents that actually provide a product specification. And it has a set of techniques which are important and detailed. There are 24 check items in the TC spec that evaluators look at to see did I actually implement according to what it says. Those include things like layering the source code and information hiding, correspondence, covert channel analysis, a whole list of some 24 of these that go into that design document as specified by the A1 criteria. But I can't run source code, so I need to actually produce at the end an end product, the actual code that's delivered in the hardware that is delivered on. And so that becomes the end product item of the deliverable product, if you will, our secure PLC. And that hardware, that includes the hardware, that hardware has to map back up to the formal top-level specification, the FTLS. And that's why segmentation is so important, because that FTLS actually has to reflect the property of the hardware. And if I didn't have that segmentation, I wouldn't be able to do that in any systematic and verifiable way. And so this is what we mean by secure by construction. It's all part of what's required by the Class A1 criteria. I'll just note a sort of extended footnote here that building that reference monitor and that formal security policy model are long, hard work. I've always taken from scratch a decade or more. And so people who want to rush in and find a solution look for lazy ways out, and they look for shortcuts. And I'll just name here some of the common shortcuts that you'll find in the literature. And these seem plausible, but they don't work. What is called, people talk about a verified operating system. That's not a verified policy model. It says nothing about the policy. It just says, oh, well, it does this functionality I asked for. Examples of that you may have heard in the literature is something called SEL4. Another approach is called a partition kernel. And again, they have ways of constructing the kernel, saying nothing about the policy. And there's an NSA project called Mills for the partition kernel, and it explicitly states in its definition that it does not include a reference monitor. That's left as an exercise to the student. For years, there's been out there things called capability hardware. And more recently, people talk about verified capability hardware. And there are a couple of DARPA-related projects over the last about a decade called Crash and Cherry that, again, focus on the hardware, don't have any verification that behaves according to a formal security policy model. And there are people that says, well, let's just do static code analysis, and that'll solve the problem. And there's something called the LDRA testbed that you'll find in the literature. These are all shortcuts to basically trying to find a quick solution to add security on to an insecure operating system. The problem with these shortcuts is none of them enforce integrity back for a PLC as we're describing here. So I just make this footnote that says, don't think that you can build what we're describing by using any of those shortcuts. They're simply not a verifiable base, as we need verifiable policy. I just wanted to quickly show the research setup that we have that implements that. We took the commercially available security kernel. It's one my company produces. If you looked at my bio, you see I've been involved in the GemSauce operating system was evaluated by NSA at Class A1. Runs on the Intel hardware with hardware rings and protection segmentation. And the picture at the left here is right out of the Intel manual. The picture to the right you'll find in various kind of GemSauce literature. But we've shown across the top the 4 integrity domains that I've been talking about. Down in the lower right-hand corner, you will notice that I've characterized the attack surfaces we talked about associated with each of these. So this is the research setup that we have. It's one that anybody can sit and build on a verifiable security kernel using the OpenPLC that we've chosen to use. So the final leg of the stool is subversion mitigation. Doesn't do any good to provide all that if it can be subverted. NIST, again, talks about this problem, and they note that there are products and work examples. I've said we've got 6 of them deployed that are resistant, highly resistant to penetration using the security kernel. And this particularly notes that Class A1 TC-SEC is distinguished by what they call substantially dealing with the problem of subversion of the security mechanisms. And again, we're just right along with those NIST guidelines in what we're doing in this research. Now, to do that, the trusted device has to protect itself in several ways, and there's a set of steps that are called out by Class A1. They do that, and we also have other sets of malware, and each one of the common malware things that you'll read about in the literature and elsewhere has a Class A1 stopper. It's a way that Class A1 stops it. And this is just a summary that says the security kernel is designed to stop malware and other kinds of subversion. That's its purpose, and it very effectively does that. So you may have seen you've certainly heard about Stuxnet, seen the pictures of how it worked. And we took and said, okay, if I were to take the results of this research and apply that to Stuxnet, could we have prevented Stuxnet? And the answer, as we've illustrated here, is definitely yes. I have a trusted device, the security kernel in its hardware, over here in the vendor of the security kernel. I have it in the vendor of the PLC, in the case of Stuxnet, I think it was a Siemens PLC, and I've got it deployed to the actual customer, in this case, the Iranian Stuxnet. Each of those has instances of this verifiable trusted device. So we want to say, well, it's interesting that I know how to do that. I know how to build those things. How could I actually deliver that? In the previous slide, recall that in the case of Stuxnet, you actually had the Iranians deploying a set of PLCs. They had to buy that from somebody. They had to get that someplace from a PLC vendor. In that case, Siemens. How does Siemens get a trusted PLC, as we've described one? And how do they get the stuff that is needed for this trusted device? And so those are the things that we have to answer when we're answering the question of how an original equipment manufacturer gets that actual delivery of a secure PLC. Our approach to doing that is the traditional one, not unique to security, not even unique to IT, but it's been around for decades, which he says that we have an underlying ecosystem that provides the things that are ultimately delivered to a customer. Something called original equipment manufacturers, the people that actually manufacture the hardware, the equipment. That model is the one that we just use in the usual way for delivering a verifiable PLC, and I'll go over a bit of how that looks. You start with a vendor that's offering the trusted device that I described. This hardware, software packaged together in some domain-specific platform. The platform might be a motherboard or a system on a chip. And depending upon what your domain of interest is, how big it has to be, whether it's a single chip or a motherboard or some other packaging of this does, at the end, I have this trusted device which implements the hardware and software of the security kernel. And some vendor produces that. I noted that in the past it's always taken a decade or more to actually produce one of those. It's one of those we used in our laboratory experiment for this test bed to show that it was feasible, but somebody has to produce that security kernel and the hardware and software and package that into something that would be this trusted device. Then the original equipment manufacturer takes that trusted device and he builds a PLC platform that he's actually going to run that hardware and software, what you might call the computer. PLCs run on computers that are not dedicated to just PLC. Typically, they take some computer, some platform, and they put the PLC on it. So somebody manufactures, so some OEM manufactures that computer. And that computer has a motherboard in it. And in this case, that motherboard could be a trusted device. Somebody takes that computer, like a PLC vendor, and actually puts an application and builds the appliance on it, in this case, the PLC. In our case, we've taken the OpenPLC source, and we put that together on that platform. Somebody like Siemens, as a vendor, could sit and do the same thing and produce their very much Siemens unique proprietary PLC that does the things that they want it to do. That vendor, having produced that, then is going to have to deliver it to customers. And so he provides it to a solution provider, an integrator, somebody who, in the case of Stuxnet, delivered it to the Iranians. And so once I have that basic foundation, the rest of that OEM cycle is something 2 to 3 years. Note that almost everything you use today is built on that. The operating systems that you buy from Lenovo are not built by Lenovo. They're built by, say, Microsoft, and they sell it to Lenovo as an OEM who puts it. So operating systems are an example of something that takes many years to develop and then gets reused over and over again, just as the security kernel is. And this is basically that traditional OEM model that can quickly lead to that. Now, we're not the only ones that recognize the power of building on that sort of a base. A decade or so ago, a former director of NSA wrote a note to some of his peers and said, we got a very high priority problem here. That is subversion of the software that we're depending on for our systems. And he said, and I see disaster looms. And he said, demand that the first solutions we can get out, if we want to get to market anytime soon, is to leverage the designs, architectures, and maintenance properties that was previously evaluated at the Class A1 level of assurance. Those exist. NSA had 3 separate evaluations, and there are other separate evaluations. And his comment was that it is the only practical way to deliver those kind of secure systems in a couple of years. That's what we need for PLCs. We have the tools to do that, and that we're not the only ones who recognize that. You know, General Farr recognized that a decade or more ago. So, to summarize what we said in our presentation, we've got a serious problem of energy delivery. Could lose 1 million lives, according to Leon Panetta. We have the technology we've had for decades that have been deployed in a security kernel technology. The criteria for that, to Class A1. And we have the standard OEM pattern for how to deliver that kind of technology to an end user. So our bottom line is that for those critical components in the energy delivery system, generators, major transformers, things like that, they need a PLC with a verifiable PLC. It doesn't have to be put everywhere. You don't have to boil the ocean. But you look at those physical critical components, and those are the ones that need a verifiable PLC. The security kernel makes that possible with a very much smaller attack surface with the 3 components we've noted that its current kernel has. The MAC, the verifiable design, and dealing with subversion. And that has put on top of that, we've in our research shown how to take the open source PLC prototype and just decompose that and reconstruct it into a running PLC that we have running today in our laboratory. And so we have not only can that OEM be modeled there, most of those half a dozen systems I mentioned that have been deployed with security kernels, they were also delivered with security kernels using that OEM model, not a PLC, but they took a security kernel by some security kernel vendor and incorporated that into a running system. So we have the pieces. So where we are today, our conclusion, there seems to be many people that say there's a need for a resilient cyber physical system. The commercial technology has been out and deployed for decades. Some of those deployed kernel-based systems have literally been deployed 3 decades and have never had a security patch. That's commercially available to provide what you call the trusted device. What we lack today are PLC manufacturers adopting that. And hope of our research and the reason for my presenting this today is to help introduce people to what has been done. People have said, well, maybe you can't really build a PLC. That's a very special kind of thing. You can't build a PLC on top of a security kernel, can you? And a year ago, people could say that because nobody had ever shown how to do that. Today, that's not true. We have the OpenPLC running on a security kernel in our lab today. And that open source, OpenPLC source is available to PLC manufacturers or anybody else that wants to use that to guide what they do. So that really is what I wanted to address today. And at this point, if someone has questions, I'll be happy to address them.
I have a question, a clarification on the Pearson safe region. Is it fair to say that, for example, it would be that the centrifuge has to operate within a certain range of RPM?
That's right. That's right. And that safe region is, since it's the only domain that can connect to the centrifuge, it would actually get the RPM ratings directly from the centrifuge, so it wouldn't get spoofed the way the Iranians were. And it would ensure that it would operate within only that certain speed. Yes. Right.
So for example, in the electrical sector, you might think of examples of field control devices, which broadly speaking might be PLCs, that they might be required to take certain protective functions, for example, trip off a line if measured frequency or voltages are out of range. So that would be an example of a Pearson safe region as well?
Yes, as I understand it. Again, I'm not a PLC or power expert, but yes, that's what I would understand.
Okay, so the issue there, I mean, this is an interesting solution, and it potentially advances the ball quite a bit. But in the case of an electrical substation, a lot of these things are context dependent, so that something that might be a safe region for a particular state, which is to say considering a number of PLCs and interconnected systems, might not be safe if there's some perturbation or some fault somewhere else in the system.
Absolutely. When I mentioned it the first time, I mentioned it as a device-specific safe region. For a given device that you're controlling, yes, your safe region application is going to be unique to that device. If you've got a rotating device like an Aurora project, that doesn't at all look like what you're using to control a large transformer.
All right, Dr. Schell, thank you very much for your presentation. Linda, anything? Okay, let's thank the speaker.